This presentation is about the splines. It includes spline representation, convex hull, control graph, spline applications, parametric continuity conditions, geometric continuity conditions, and spline specifications. A spline is a flexible strip, this one, from point here to here, which is used to produce a smooth curve through a designated set of points. Several small weights are distributed along the length of the strip. The term spline curve originally referred to as a curve drawn in this manner. In this drawing, we can see this one is a spline and these control points, again control points, these all are control points represented by dots. And splines produces smooth curve. This one is also a spline curve, and this dot indicates the control points. This one is also represented a triangular spline curve. And we can mathematically describe such a curve with a piecewise cubic polynomial function. And in computer graphics, the term spline curve refers to any composite curve formed with polynomial sections satisfying specified continuity conditions at the boundary points. And this is a spline curve. This is a curve. This dot represents control points. 4 control points are here. This is a starting point, starting control point. This is the ending control point. And a spline curve is specified using a set of control points. There are two ways to fit a curve to these points. Two types of spline curves are interpolation and approximation. Interpolation means the curve passes through all of the control points. These red dots represented by control points, and this curve passes through all of these control points. This one is another spline curve interpolation, that is, these are all our control points, and this line passes through this control point, this one, and all the control points. Like this one is the last control point. And in the case of approximation, the curve does not passes through all of the control points. This one is an example for approximation. This one is a control point. This another one. Then this curve may not pass through all the control points. This one is starting point and this one is the ending point. And another term is convex hull. The boundary formed by a set of control points for a spline is called a convex hull. This is a spline P0, P3, and boundary formed is P0, P1, P3, P2. This one is a boundary of the spline curve P0, P3. Each control point is either on the perimeter of the hull or inside it, bound in the control points. Here all control points lies in the boundary. And here P0, P3 is the spline curve, and the control points are this one, boundary is P0, P1, P2, and control points are this one, P3 and P0. This control point is inside this boundary. And another term is control graph. This is a polyline connecting the control points in a specified order. That is, this control points is P0, P3, and the control graph represents it is connecting this one, P0, P1. P0, then P1. Next one is P2, P3. This is a specific order. Then this control graph is P0, P1, P2, P3. Usually displayed to help designers to keep track of their splines. Here control points we can represent P0, P1, P2, P3. That is the control graph. And the applications of spline are, these interpolation curves are commonly used to digitize drawings or to specify animation paths. It is mainly used to specify the animation paths. And these approximation curves are primarily used as design tools to structure object surfaces. A spline curve can be defined and it can be modified and manipulated with operations on the control points. You can do all the operations on control points, and according to that the spline curve is manipulated. And by interactively selecting spatial positions for the control points, a designer can set up an initial curve. After the polynomial fit is displayed for a given set of control points, the designer can then reposition some or all of the control points to restructure the shape of the curve. That is, by changing the control points, a designer can restructure the shape. In addition, the curve can be translated, rotated, or scaled. That is, this type of geometric operations can be applied to the curve. And CAD packages, that is computer aided design packages, can also insert extra control points to aid a designer in adjusting the curve shapes. And this is the parametric continuity condition of the spline. For smooth transition from one curve section to next curve section, we put various continuity conditions at connection points. Here this is a spline, then this is the connection point, this one is another one. Let the parametric coordinate functions as x equal to x of u, y is equal to y of u, z is equal to z of u, where u is in between u1 and u2. Then this zero order parametric continuity, C0, means simply curve meets. That is, the last point of first curve section and the first point of second curve section are same. See this one. This one is a curve section, and this one is the first point, starting point. This one is the last point, ending point. And it's for this second curve, this one is the first point. That one is the last point. This means that zero order parametric continuity says that this last point of first curve, this one, is same as the first point of the second curve. That is, this one is connected. And first order parametric continuity C1 means first parametric derivatives are same for both curve section at intersection points. This one is intersection point. And second order parametric continuity C2 means both the first and second parametric derivative, first derivative and second parametric derivative, or two curve section are same at intersection. At this intersection, first derivative and second derivative are same. Then higher order parametric continuity is can be obtained similarly. That is, Cn we can calculate. First order continuity is often sufficient for general application, and some graphics packages like CAD, computer aided design, requires second order continuity for accuracy. And geometric continuity conditions. This is another one. Another method for joining two successive curve sections is to specify condition for geometric continuity. Here, zero order geometric continuity represented by G0 is same as parametric zero order continuity, that is two curve sections meets. That is this one. End point of first one is the starting point of second curve. Then first order geometric continuity G1 means that the parametric first derivatives are proportional at the intersection of two successive sections. Here parametric first order derivative is proportional. That is, this curve is proportional to this one. It is not necessary that its magnitude will be equal. This may not be equal, that the length of this one and length of this one may not be equal. That is, in other words, tangent direction must be same, magnitude may differ. And the second order geometric continuity G2 means that both the parametric first and second derivatives are proportional at the intersection of two successive sections. That is, first derivative and second derivatives are not same, they are proportional for first curve and second curve. It is not necessary that its magnitude will be equal. The geometric continuity curve is pulled towards the section with the greater tangent vector. That is, C1 is proportional to this C3. The difference is that a curve generated with geometric continuity conditions is similar to one generated with the parametric continuity, but with a slight differences in curve shape. With the geometric continuity, the curve is pulled toward the section with the greater tangent vector. And spline specifications. Three types of specifications. We can state the set of boundary conditions like this. X of u is equal to ax u cube plus bh u square plus ch u plus ds, where u is in between 0 and 1. Then in matrix format, h of u is equal to matrix u cube u square u u1 into matrix column matrix ax bh ch ds. And using blending functions or basic functions, we can represent this as h of u is equal to sigma k is equal to 0 to 3 gk into blending function of k of u. Here gk is are the constrained parameters, that is control point coordinates or slope, and bf k of u is the blending function. And this is an example, an approximation spline surface for a computer aided design application in automotive design. Thank you.